Hello everyone, hopefully you have your note sheets in front of you and you're ready to start learning about Chapter 9. We're going to start in the chapter called Sampling Distributions. This chapter is pivotal for the next several chapters. Basically everything we do in the course from here on out is going to have something to do or related to this chapter. So please pay attention, take notes, and ask questions tomorrow. So to get us started, there's a couple definitions you need to know. First, a parameter. A parameter is a number that describes the population. It is a fixed number. And in practice, we generally do not know its value because we can't examine the entire population. I've talked about this in class before, how if I want to know, say, the average cholesterol of American men, there's no way I could possibly know that number unless I go out and actually interview every single American man, which is just not feasible. That would be an example of a parameter. It is a number. It exists. There is an average number or an average cholesterol for adult American men out there, but nobody knows it, and there's no way to really find it, and that's what we use parameters for. Generally, we use Greek letters to represent parameters. So when you see something with a sigma or any kind of Greek letter, that's generally talking about a parameter. Okay, the next definition you want to write down is a statistic. A statistic is a number that describes a sample. The value of a statistic is known when we have taken a sample, but it can change from sample to sample. So that's the main difference, is a parameter is unknown. It exists, we just don't know it. Whereas a statistic we know because we've taken a sample, we've asked 100 people or 1,000 people or whatever it is, and we have that data in front of us, and we can actually go about calculating the mean or the standard deviation or whatever it is we want to know. That is a statistic, and it will change. If I select 100 people today and then I select a different 100 people tomorrow, the value of the statistic will change from sample to sample, but it is something that we can find and we can know. We often use statistics to estimate unknown parameters. So I've said that you can never know what a parameter actually is, and we use statistics to help us estimate them, to help us figure out how close we are. This often, it will use variables. So it uses x bar or p hat or something like that. It's non-Greek. We use variables, non-Greek variables, to represent statistics. So let's compare these two things. So a parameter, you can see the different symbols we use. The first one, mean, is mu. Standard deviation is sigma, and the proportion is called rho. And sometimes we call parameters true, and we call them the true mean or the true proportion. A statistic, for the mean we use x bar, for the standard deviation we use s, and for the proportion we use p hat. And sometimes we call the statistics a sample, meaning sample mean, sample proportion, etc. That leads us to sampling variability. If you're creating or taking a bunch of different samples, the mean of each sample will change from sample to sample. Hence, sampling variability happens. To make sense of sampling variability, we ask the question, what would happen if we took many, many samples? So to answer this question, we would do the following. We would take a large number of samples from the same population. We would calculate the sample means or the sample proportion, depending on which we're interested in, for each sample. Then we would make a histogram, and we would examine the distribution for the shape, the center, the spread, and the outliers. Remember CUS? It's coming back now. So we're going to be using CUS when we start talking about these distributions. So the key thing is, if we're trying to figure out what a parameter is, we need to do samples. But we can't just do one sample, we have to do multiple samples. The statistics change from sample to sample. This is variability. We need to make sense of that variability in order to estimate what the actual parameter is. In practice, it's too expensive to take many samples from a population, so therefore we use simulations, and they may be used instead of taking many samples to approximate the sampling distribution. And probability is often used to obtain an exact sampling distribution without simulation. So sampling distribution. A sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. Okay, so it's like a probability distribution in that you make a chart and it has all the different probabilities. So it studies the sample space. It has every single possible probability. A sampling distribution of a statistic is the distribution of the values taken by the statistic in all possible samples of the same size from the same population. Alright, so here's an example. Are any of you Survivor fans? You ever watched the TV show Survivor? So, television executives and companies who advertise on TV are interested in knowing how many viewers watch particular TV shows. According to the 2001 Nielsen ratings, Survivor 2 was one of the most watched TV shows in the U.S. during every week that it aired. Suppose that the true proportion of U.S. adults who watched Survivor that year was 37%. Now remember, we can't possibly know that. That's a true proportion. That's a parameter. We can estimate it, but we can't possibly know it. We know it exists. We know that number's out there. We just don't know what it is. Okay, but suppose, let's just pretend for the purposes of this example, that the true proportion is 37%. First, suppose we did a survey of 100 people. And then we did this survey 1,000 times. So I'd randomly select 100 people. I'd figure out the proportion of the 100 that watched Survivor. Then I would do it again, and then I would do it again, and then I would do it again. And I would take that number, that proportion, every single time. What that might look like then is it might look like this. So what you have here is you have a histogram. This is the sampling distribution for simple random samples of size n equals 100. So it took the 1,000 different samples, and every spot on the histogram represents one sample. So you can see that a few of the samples, maybe 5 of the samples, had a 22% proportion. A couple of the samples had like a 10%. It looks like about 110 of the samples had 31%. 200 samples had 34%. So that is a selection of all of them. And you can get an idea of what that looks like. That should look familiar to you. It should look approximately normal. That hopefully was the first thing that you thought when you saw that. Wow, that looks like a bell curve. That looks normal. Now, suppose we did this for a size of n equals 1,000. So now I've changed my sample size from 100 people to 1,000 people. And now I get this, right? That's what you see in front of you. Looks a little bit different, right? You might think to yourself, well, that looks totally different than the 100 did. But let's focus in a little bit closer. I'm going to zoom in and I'm going to change the scale. So notice that at the bottom, where I'm counting by threes. If I change the scale and I count by ones, notice that again it looks like it's approximately normal. It looks like a normal distribution, and it has a center at 37%. Now remember, for the purposes of this problem, we are proposing that the true proportion was 37%. And based off of this, you can see that the center of our 1,000 samples is right around 37%. And because the sampling distribution is centered at the true value, there is no systematic tendency to either overestimate or underestimate the parameter p. Right? And that's what we want to have happen. We want to have the center being somewhere around the true proportion, and that is generally what happens, and that's what allows us to make these predictions. What this is this tells us that our sample proportion, p hat, is an unbiased estimator of the population proportion. Okay, so that's a very important definition, and I'm going to bring it back again in another slide in a little bit. But it's very important to understand what exactly an unbiased estimator tells you. So if we're talking about simulations, we use simulations to illustrate the general behavior of samples of fixed size. So say we took 10,000 samples. The top green one is sample size 30, the middle purple is size 60, and the bottom yellow is size 120. They're generated from this uniform distribution, and they calculated the means each time, and then each mean is graphed on the histogram. Probability histograms will be created for each of these distributions. And notice that all three of them are essentially normally distributed. Further, the variability decreases. You want to pay attention to that. When the sample size is small, it has large variability. Right? If you look at the green one is very spread out. If you look at the purple one, not as spread out. If you look at the yellow one, nowhere near as spread out. The larger the sample size, the smaller the variability, which means the smaller the standard deviation. So keep that in the back of your heads. Smaller sample size, bigger spread, more variability, bigger standard deviation. Bigger sample size, smaller standard deviation, less variability. Now, from there, another type of simulation. So to further illustrate the general behavior of samples of fixed size n, 10,000 samples, each of size 4, 16, and 32 are generated. Now we started off in this case with a skewed distribution. So even though we started off with a skewed distribution, if the sample size is small, like n equals 4, it's going to produce a skewed sampling distribution. However, as the sample size gets bigger, the sampling distribution gets less and less skewed until eventually it becomes almost normally distributed. So what this is telling us is that even if our distribution starts off being very skewed, either left or right, if I create a sampling distribution from that original skewed distribution, if the samples are big enough, I'm going to wind up with something that's approximately normal. And that's very key, because that then allows us to use all of the rules and all the probability calculations that we've been talking about in regards to normal distributions. We can't use any of those rules on skewed distributions, but if we know that by taking a large sample and doing that many times, we are going to wind up with a nice and approximately normal sampling distribution. Okay, so here's a couple more definitions you want to write down. An unbiased estimator. A statistic used to estimate a parameter is unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. We call this statistic an unbiased estimator of the parameter. Alright, so what that means is the statistic, we call it unbiased if we take the mean of the sampling distribution and the mean of the distribution is equal to the true value. Variability of a statistic is described by the spread of the sampling distribution. The spread is determined both by the sampling design and the size of the sample. Larger samples give smaller spread. So as long as the population is much larger than the sample, say at least 10 times as large, the spread of the sampling distribution is approximately the same for any population size. So for large samples, we're going to get less variability, which is a good thing. Small samples give more variability, which is not always a good thing. Alright, so we're getting close to the end. We can think of the true value of the population parameter as a bullseye on a target. The sample statistic is the arrow that's fired at the target. Both bias and variability describe what happens. So here's an example of something that is high bias and low variability. Bias, we've talked about bias in previous chapters, but I'll just remind you. Bias means that our aim is off and we consistently miss the bullseye in the same direction. So you can see that they are very consistent. They're hitting the same spot, it's just nowhere near the bullseye. So it's like their sights are off, right? They're consistently being pulled in one direction. So what you have is you have a high bias and a low variability in this case. Here you have an example of low bias but high variability. So low bias because all the dots are centered around the middle of the target, but they're still very spread out. Right? High variability means repeated shots are widely scattered. This is an example of both high bias and high variability. Right? So all the shots are pulled in the same direction and they're also all very spread out. And finally, this is what you want. This is the ideal. You have low bias, they're all hitting the same center of the target, and they're all very tightly grouped, and that's low variability. So the lesson about center and spread that I want you to remember, if you're given a choice of statistics to estimate some parameter that's unknown, you should always choose one that has no or low bias and minimum variability. Right? That's what you want. So here's an example. Take this histogram and I want you to label it. I want you to think about what type of bias and variability does it have. Is it high bias, high variability, low variability? Okay, you should have an answer. I want you to think of an answer in your head. Okay, so this is an example of large bias and large variability. Notice if you think of this as a balance beam, it's heavily weighted to the left, so that's your bias, and it's also very spread out, so that's your variability. What about that one? Have your answer. That one is low bias and low variability, right? It's balanced in the center, and it's very tightly grouped. What do we think about that one? All right, that's small bias but large variability. It is centered, right? It's centered over the middle, so it is balanced, but it's very spread out. So centered means small bias, spread out means large variability. And then the last one, large bias, it's heavily pulled to the right, but small variability because it's so tightly grouped. For tonight, I want you to do these problems in your textbook, chapter 9, so 1, 2, 3, 4, 10, and 11, and then that should not take you very long. And that brings us to the end.